In this lesson, we will formalize the function that we have used informally in the first lesson, the family of exponential functions. We will define them, we will check the two types of graphs that represent them, and we will cover their main properties. The skill you need to master the lessons are simply a good recall of the terminology and notation about functions. Let's begin by the definition of an exponential function. Here is a statement defining an exponential function. We call y equals a to the x the exponential function base a. A must be positive and different than 1, while x is a real number. As usual in an exponential notation, a is called the base and x the exponent. I will use exp subscript a of x to represent the function a to the x. For example, if I write exp base 2 of x, that simply means 2 to the x. Or if I write exp base 5 of x, it will mean 5 to the x. All right. Let's go over 4 important remarks about this statement. The first remark is about the exponent x. X is the real number. Now, this is not something we can define in this class, so we will have to assume that it has a meaning. Again, what does 2 to the root 5 means, or 3 to the pi? These are questions we can't really go in detail. Let's just assume this is defined. The second remark is about the base a. We have to assume that in the exponential notation, the base a is positive and different than 1. Let me first focus on positive. It is important to assume we take a positive number, because if you take a to be negative, then sometimes an exponential with a real exponent could be not real. The output of this expression could be a non-real number. That means a complex number, but we have not seen this year what a complex number is. So again, very important to assume that the base is positive. The third remark is about the fact that the base cannot be 1. Why is that so? Well, what do you have if you take a base equal to 1? If a is 1, then the function is just 1 to the x. 1 to any power is just 1. And such a graph is not very interesting. It's just a horizontal line. The reason why I am not looking at the base 1, it's because this graph doesn't pass HLT. It does not have an inverse. And so we will ignore a base equal to 1. Finally, the last remark is that in these family of exponential function, the input is at the exponent. This is the input of the function. Let me remind you that in the previous unit, we saw a family of monomial function. We wrote them as x to the n, and we said n had to be a natural number. In the previous unit, we've also seen other types of exponent. We've looked at positive rational exponent and negative number exponent. Well, you can show that you can actually extend the family of monomial function to a broader family of power function. In a power function, you allow the exponent to be a real number. Okay? So we have a family of monomial functions right here, and it's included in a broader family of power function where the exponent is a real number. Now, these power functions are very different than the exponential function. These two families have nothing to do with each other, because in a power function, the input is at the base of the exponential notation, while in an exponential function, the input is at the exponent in the exponential notation. Very different. To make sure we can differentiate between these two family of functions, let's go over the first series of examples. All right, in the examples we're going to go over, I'm asking you if the given function is an exponential function or a power function. So basically, just spot where the input is. For the first function, the input x is at the exponent, and so this function is an exponential function. Second example, here, this function has an input called t, and I see that t is at the base of the exponential, so this is not an exponential function. It is a power function. Next example, here the input is called u, and u is at the exponent of the exponential notation. So this is an exponential function. Next example, this time my input is called s. S again appears at the power of the exponential notation. The base is pi. Okay, well, that's just a real number. Okay, so this is another exponential function. Next example. All right, in this example, the input is called b. I know it's not very common. Why not? Where's b? Right here. B is at the base of the exponential. Here's the exponential piece, and b is at the base of it. So this is a power function. Finally, the last example in this series. In this last example, I call the input c, and I'm looking at this expression. This is where my exponential is, and c appears at the exponent. Therefore, this is an exponential function. Let's continue to the second series of questions about exponential functions. In this second series of examples, the question relates to the work we've done in the second video about exponential functions. So I'm given a function. It is an exponential function. What is the initial value of the function? Well, for an initial value, the input has to be 0. So what is f of 0? It's 25 times 3.5 to the 0. Anything to the 0 is 1, so it's just 25 times 1. So it is 25. And in general, if you have the function f of x equals b times a to the x, the initial value will be b, this number that multiplies the exponential part of it. Okay, so my initial value is 25. And then, is it an increasing or decreasing function? What do you do to 25? You multiply by 3.5 to a power. Now remember, when you multiply by 3.5, you are increasing 25. So it is increasing. It's increasing by what percent? Well, 3.5 is 1 plus 2.5, and 2.5 is 250%. This is again some work we've done in the second video. So this function describes an increase of 25 by 250%. Now, if x is 1, it's an increase by 250%. If x is 2, I'm going to increase by 250% twice. If x is 3, I'm going to increase by 250% 3 times, so on and so forth. Let's go to the second example. Okay, this time the initial value is 0.25. So 0.25 is an initial value, and I multiply 0.25 by 1.25 to the power of t. When you multiply a number by 1.25, you are increasing the number. By how much? 1.25 is 1 plus 0.25. 0.25 is 25%. So it's an increase by 25%. Again, if t is 1, you just increase by 25%. If t is 2, you increase by 25% once, and then by 25% again, so on and so forth. Next example. Okay, here the initial value is 7.5, and my exponential is 0.6 to the power of s. This time I call the input s. Now 0.6, we know this is going to be a increase, right? It's smaller than 1. It's 1 minus 0.4, so it is 100% minus 40%. So it is a decrease by 40%. All right, let's move on. Last example in the series. What is the initial value of this function? It is 1.25. And you multiply by an exponential whose base is 2, right? So basically multiplying by 2 is an increase. 2 is 1 plus 1, so this is 100%, right? So you are increasing 1.25 by 100%, and you're doing so successively depending the value of s. All right. As I mentioned, one of the novelty about exponential function is the fact that the exponents are real numbers, okay? It is an important jump to go from rational to real number exponents. But even if we have not detailed this jump, the piece of excellent news is that the properties that were true for rational exponents are also true for real exponents. Let's quickly recall these properties. Here we go. You should be very familiar to every property on this list. The only thing that you didn't know until now is that they are all true no matter what you put at the exponent. Natural number, integers, rational numbers, or real numbers. All these properties are true for any of these exponents. Let's now consider the graph of an exponential function. Basically, there are two types of graph depending on the value of the base. All right, the first function I want to look at is f of x equals 2 to the x. This is a very nice exponential that will give us a lot of points, okay? So if the input is -2, what is f of -2? Well, f of -2 is 2 to the -2. 2 to the -2 is 1 over 2 squared, and so it is 0.25, 1/4, right? F of -1, f of -1 is 2 to the -1 power, which is 1 over 2, so it's 0.5. F of 0 is 2 to the 0, which is 1. F of 1, 2 to the 1 is 2. F of 2, 2 squared is 4. And f of 3, 2 to the 3 power is 8. Okay, let's plot these points in the given graph right here. So f of -2 is 0.25, it's about here. F of -1 is 0.5. F of 0 is 1. F of 1, 2. F of 2, 4. F of 3, 8, like that. If you connect the point, you have a graph that looks like this right here. If you were to compute more points in the negative direction, you'd be closer and closer to the x-axis. All right, let's look at the second function. For the second function, I've changed the base to 1/2. I'm looking at the function g of x equals 1/2 to the x. So if the input is -3, what is 1/2 to the -3 power? We've done this work before. You flip the fraction and you turn the power into a positive. So this is 2 cubed, which is 8. If the input is a -2, 1/2 to the -2 power is 2 over 1, so just 2 to the second power, so it is 4. Oh, there's a parenthesis right here. If the input is -1, 1/2 to the -1 power is just 2, 2 over 1, which is 2. 1/2 to the 0 power is 1. 1/2 to the 1 power is 0.5. And 1/2 to the second power, 1/2 to the second power is 1 squared over 2 squared, so it's 1/4 or 0.25. Okay, let's plot this point in the given system. So -3, 8, -2, 4, -1, 2, 0, 1, 1.5, 2.25. You could show again that if you were going further in the positive direction, the point would get closer and closer to 0. The y-coordinate of the point would get closer and closer to 0. If you connect the dot, you have these kind of graph. The two graphs I've just showed you are very typical of the two families of graph exponential function have. One had a base above 1, that was 2 to the x, the graph went like this, and the one we just covered had the base smaller than 1, and the graph went like this. Let me show you more graphs of exponentials. So in this graph, I've represented the function y equals a to the x. Let's now derive a few properties of these exponential functions simply by looking at their graphs. First, we see that every graph goes through the point 0, 1. This is simple to explain. If you make the input 0, then a to the 0 is 1, no matter what the base is. Second, if the input is 1, then a to the 1 is a. And so every graph will go through the point 1 and then the value of the base. This is, for example, exponential base 5. So it goes to the point 1, 5. This is exponential base 3. It goes to the point 1, 3. When the base is smaller than 1, these points are more difficult to graph. It is more interesting when the base is smaller than 1 to take the input equals to -1, because in this case, when the input is -1, a to the -1 is 1 over a. So for example, if a is 1/2, then 1 over a is 2. So we have this point right here, -1, 2. If a is 1/3, 1 over a is 3. And so we have this point right here, -1, 3. So again, depending on the value of the base, sometimes it's better to take an input equal to 1. Sometimes it's better to take the input equal to -1. Third property. When the base is above 1, the function is increasing. When the base is above 1, the function is increasing, while when the base is smaller than 1, the exponential function is decreasing. All right, we saw that when we graph 2 to the x and 2 to the -x. Next property. Every single exponential function has a graph above the x-axis. And actually, the last property will be that the x-axis is the asymptote. So the graph is not equal to the x-axis. What does it mean? It means that no matter what the base is or the input is, an exponential base a will be above 0. So a to the x is always a positive quantity, never negative. Finally, the last property is the asymptote property. We notice that the x-axis is asymptote to all the graph. More precisely, when the base is above 1, the x-axis, or the line y equal to 0, that's the x-axis, is an asymptote as x approaches negative infinity. And when the base is smaller than 1, then the x-axis is an asymptote as x approaches positive infinity. You must be familiar with all these properties. I have written them in your notes. Let's sketch a few more graphs to understand how to sketch an exponential function. Okay, in the same graph, I'm going to sketch 3 to the x and 1/3 to the x. Let's start with 3 to the x. So if x is 0, 3 to the 0 is 1. Goes through this point right here. If x is 1, 3 to the 1 is 3. So it goes to the point 1, 3. And if x is 2, 3 squared is 9. So it goes to the point 3, 9. If x is -1, 3 to the -1 is 1/3. So -1 would be 1/3 right here. This is an increasing graph. It does have an asymptote on the negative side of the axis. Here is the graph 3 to the x like this. Okay? And it goes very, very fast, increasing very fast right here. This is y equals 3 to the x. All right, now let's do 1/3 to the x. If x is 0, 1/3 to the 0 is 0. If x is 1, 1/3 to the 1 is just 1/3, right? So the graph would be right here. If x is -1, 1/3 to the -1 is just 3 over 1, which is 3. -1 is 3 right here. If x is -2, 1/3 to the -2 is 3 over 1 to the second power. 3 over 1 is just 3. That's 3 to the second power, so it is 9. Okay, so -2, 9 is right here. Okay, now again, I will have an asymptote on the positive side of the axis. Let me connect my point like so. And then right here, let's get the asymptote like so. Here we go. You can see that these two graphs seem to be symmetrical with respect to the line x equals 0. This is actually true. And this is based on a very simple property. You know how to reflect a graph through the y-axis. If you take, for example, the function f of x equals 3 to the x, how do you reflect it through the y-axis? Well, you would define the function f of negative x, right? When x becomes negative x, this is the reflection through the y-axis. Now, f of negative x would mean 3 to the negative x, which is 3 to the -1 to the x, which is 1/3 to the x. So in general, the relation between a function a to the x and the function y equals 1 over a to the x is that of a reflection through the y-axis, because to go from here to here, it's the same as replacing x by -x, as we just saw right here. Okay, let's do a few graph shifting now. All right, I want to graph this function starting with 2 to the x. So let's graph 2 to the x, 2 to the x, 2 to the 0, 1, 2 to the 1, 2, 2 to the 2, 4, and 2 to the 3, 8. Okay, this is a very nice function. It has a lot of points. 2 to the -1 is 1/2 actually. Okay, so here we go. This is our first function that we are going to move. All right, this is y equals 2 to the x. Now, the first thing that you're going to do when you see that, from y equals 2 to the x, you're going to be going to y equals 2 to the x minus 4. You know what it does. This is 4 units to the right. 1, 2, 3, 4. This point goes right here. This point goes right here. This point goes right here. This 1/2 goes right here. And finally, the 8, y equals 8, goes right here. Here we go. This is a graph 2 to the x minus 4, and it's very close to the x-axis right here. Okay? All right. Then what do? Then we have the graph from 2 to the x minus 4, we go to y equals 3 times 2 to the x minus 4. We know what that does. It's going to multiply the y's by 3 units. Okay, so this is 1/2. 1/2 times 3 is 1.5. This is 1 right here, right? 1 times 3 is 3. This is 2. 2 times 3 is 6. This is 4. 4 times 3, oops, I've lost it, right? So I'm just have these 3 points. That's not too many, but hey, that's a dilation by a factor of 3 that makes me lose many points right here, right? And then right here, this graph actually is above the blue, right? I multiply by 3, it's above the blue. Then what is the next graph? I multiply everything by -1, right? So it's -3 to the 2 to the power of x minus 4. This operation will flip the graph across the x-axis. So I'm going to take all the points on the red graph and I'm going to flip them across the x-axis. This one 6 up goes to 6 down. This one 1.5 up goes to 1.5 down. Again, I only had 3 points. The other ones have disappeared. So this is the graph I have right now. And I think there is one last graph, right? One last graph from here I go 4 down, so it is y equals negative 3 times 2 to the power of x minus 4 minus 4. I know what to do. I move 4 down, so 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right, so the final graph I have is this one. Before I go further here, there's a feature I need to pay attention to. It's a horizontal asymptotes, right? I did have the horizontal asymptotes for all the previous graph, but when I move down by 4, my horizontal asymptote is also going to be moving down by 4 units, right? So 1, 2, 3, 4. Here's the horizontal asymptotes I have to respect now. And so now I can just draw my graph like so. Here we go. All right. So I think this is enough for this lesson. I hope everything was clear. Thank you for watching.